Okay.
Okay, so for today, we are going to be finishing up with our arteries and arterioles. We're going to finish up with understanding how our arterioles especially are controlling blood flow to our different organ systems. And hopefully we will get a bit into our capillary system and start thinking about exchange across capillary walls between our blood plasma and our tissue. Okay. So last time when we were talking, we had talked a little bit about our local intrinsic controls of arteriolar radius and therefore of arteriolar resistance. I'm just going to flip us back for a second. So that was this. We were talking about our active and reactive hyperemia. So we were talking about how our blood vessels, our arterioles, tend to dilate to get more blood flow to tissue that is metabolically active, which we would be able to sense because we can see that there's low concentration of oxygen, high concentration of waste products like CO2, and that we have a similar situation if we think about what happens after we have a blood clot, after we have some type of compression. We'd have a similar depletion of oxygen, buildup of CO2, and your blood vessels would react similarly once there's a release of that pressure, that blockage, whatever cut off blood flow. You'd similarly see your body try and make up for it by rushing more blood to that area. So those were two of our types of intrinsic control of blood flow that we talked about on Wednesday. So we're going to talk about our third type right now, which is, I almost think of this as like just a stretch response. So the myogenic response or myogenic autoregulation of blood flow is a response of the vascular tissue of the smooth muscle, essentially in those blood vessel walls. Okay. So formally, it's a change in vascular resistance in response to the stretch of blood vessels in the absence of external factors. But what we're really thinking about is just kind of like they stretch, they kind of bounce back. Fundamentally, that's kind of what's going on with our myogenic response. So what we would see happen is as we have this myogenic autoregulation of blood flow. So imagine we have an increase in perfusion pressure. So perfusion pressure is just that another word for that pressure difference across our blood vessel. All right, so we have an increase in pressure on either side of our arteriole, for example. Therefore, we're going to have an increase in blood flow going through that arteriole. Since you have an increase in that pressure and an increase in that flow, this is going to have some effect on those walls, right? They're going to start to expand a little bit as there's more stuff going through them. So there's increased pressure stretching that arteriolar wall. Okay. When we stretch the muscles in that arteriolar wall, because we're sending more flow through them, an inherent property of them is that they don't really like that, and they're going to try to bounce back a little bit. And that's the sort of big picture explanation of what's going on here. So that's just an inherent property of smooth muscle, is that it doesn't want to be stretched out too much. Okay. So that response, that bouncing back, so we put more blood flow through because we had more pressure. That flow stretched out our blood vessel a little bit. The smooth muscle doesn't like it. It starts to bounce back. I've just made my hands get smaller. I've made this circumference get smaller. So this is vasoconstriction. As that smooth muscle bounces back, it's making that radius of that arteriole a little smaller again, which is raising its resistance, which is now starting to cut off that increase in blood flow that we may have observed. The overall goal of this is actually just to keep blood flow constant. So this is really a negative feedback kind of response, right? Because it's a response to an increase in perfusion pressure, so an increase in that delta P, an increase in that pressure gradient that caused an increase in flow. We don't want the flow to increase too much, so the blood vessels bounce back a bit, constricting, leaving us with a hopefully nice kind of steady blood flow instead. So our other two methods of our intrinsic control of blood flow were about creating dilation, right? Getting more blood flow to this region. And so this one is about responding to an increase in blood flow, getting us kind of back to normal. So this is kind of the opposite. We could see that in flowchart form as well. So one of our nice flowcharts from our book, if people like flowcharts. So here we see an increase in perfusion pressure, which is really just the same as that delta P, right? So that would be for our whole system was our mean arterial pressure minus our central venous pressure. That's just an example of something that might be described as a perfusion pressure. We're talking about an organ. We talk about what's going into the organ versus what's coming out of the organ. That's perfusion pressure. So we know that flow is equivalent to our difference in pressure divided by our resistance. So as we increased our perfusion pressure, we saw an increase in flow. So that's here. So that's one of the effects of that increase in perfusion pressure. If we think about a tube, suddenly we increase the flow. This means we are also increasing the stretch of the smooth muscle in the wall. So that's why we're paying attention to this little up sign. Okay. So then the response would be basically like here. This is the bouncing back portion of that myogenic response. So in response to stretch, we're constricting, okay? So as we increase constriction, an increase in constriction means we're decreasing our little r radius, which is inversely proportional to our resistance. Our big R was not an equal sign, just an approximation, inversely proportional to our radius. So if our radius goes down, our resistance goes up. Okay, so that's how we get to here. Right. And then we can go back to our main equation again, right? So our flow equivalent to our difference in pressure, that perfusion pressure, divided by our resistance. So now if we are increasing our resistance, I'm going to pick another color. Now that we've increased the resistance, this is going to create a decrease in the flow. Okay. So this is all a negative feedback adjusting that flow rate through whatever part of the body we're talking about. Okay. Questions on this part? I realize I just made a bunch of scribbles, but I'm just walking you through how you would think about this, basically. Cool. Okay. So we've mentioned that one of the reasons that we want to regulate resistance is because we're regulating blood flow to specific organ systems. And one of our key examples of this is what happens when you are at rest versus when you're exercising. So your cardiac output, 5-ish liters per minute at rest. When you exercise, you have a lot more blood flow, a lot more cardiac output. So here we have 25 liters per minute. And we can see that there's a big difference in how much blood is going to each of your systems in these two situations. So a bunch of this is going to be due to our extrinsic controls of resistance and arterial pressure. We're going to think about these extrinsic controls now. So extrinsic coming from somewhere else. Our previous three were all really local. It was all about our dissolved gases essentially hanging out in that interstitial fluid, or just how stretched out that smooth muscle is in the case of our myogenic autoregulation. Mouthful, but myogenic, myo muscle, genic, like what's generating it, autoregulation, self-regulating. So all of those are local intrinsic factors. So our extrinsic factors are going to be from somewhere else in the body. So we're thinking nerves, we're thinking hormones when we're thinking extrinsic controls. Okay. So far, we know that our flow is going to be equivalent to our difference in pressure, which we might just write out as delta P. Sometimes we're going to abbreviate it as our mean arterial pressure, We just called it perfusion pressure in a different slide, but fundamentally, we're just talking about this pressure gradient, this difference on one end versus the other end. Then we divide it by our resistance, which is just how much forces they're trying to stop this. Most of that coming from how small or large the radius of our blood vessel is. There are other factors that affect resistance as a property of physics, but for our cardiovascular system, it's mainly radius. Okay. So then we also saw previously, and I'll write this part out, right? We can substitute in physiologic variables to this general equation for flow. So flow, when we're talking about the cardiovascular system, that is our cardiac output, okay? So the blood coming out of our heart is the flow we're talking about. Okay. Our difference in pressure is our arterial pressure minus our venous pressure, but our venous pressure is negligible, almost zero, in the case of our systemic circuit anyway. So we can just use the arterial pressure. So mean arterial pressure is our delta P for the system most of the time. And then we are going to divide by our resistance, and our measure of resistance in the cardiovascular system is just adding up all the resistance everywhere in your body, which is our total peripheral resistance, our TPR. So that's not a new equation, that's just putting in new names for these variables, right? So we're saying specifically where we would measure this in a body, same concept though. We are moving towards understanding how we regulate blood pressure. That's going to be part of our point of learning about the cardiovascular system. Blood pressure problems are really common. So blood pressure can be related to this mean arterial pressure up here. So this next bit is just reformatting this equation so that we can focus in on that piece. Okay, so we can reshape this equation. We want to know about our mean arterial pressure specifically. We can just take our resistance and move it over to the other side of the equation, right? We're dividing on the right-hand side here. So we could just multiply that out on the other side, which would give us TPR by cardiac output equals map, since they're equivalent, either on the left or on the right. So that's how we reshaped and got to this. Okay. And then to get to this final form, what we've done is put in information that we know about cardiac output from our study of the heart. So we know that cardiac output is how much blood is coming out of your heart per minute. Cardiac output, blood per minute. So we know to get that, we use our stroke volume, which is how much blood is coming out of your heart during the cardiac cycle, during that ventricular ejection phase. How much blood are you squeezing out every time your heart beats? But we want to know per minute. So we also have to know how many heartbeats per minute, which is our heart rate. Okay. So that's how we're getting to this larger, longer form. We've taken this stroke volume by heart rate and put it in for cardiac output. Right, so we've just broken down that concept, which is how we get to this larger equation that our mean arterial pressure is going to be equivalent to our stroke volume by our heart rate by our total peripheral resistance. So as we're moving forward, and we're eventually going to be using these concepts to think about regulation of blood pressure, we're just pulling out these pieces now. So this is kind of like your hint for the future that we'll be thinking about resistance and its effects on blood pressure. But we know that a lot of these extrinsic factors that we're about to talk about do also affect stroke volume and heart rate. So we're going to have a lot of different effects in our body working in concert kind of to affect our blood pressure overall. But we will have a whole separate set of lectures on the mean arterial pressure and its regulation. That's just where we are now. Okay. So we're thinking about extrinsic control. So we want to remember a couple things from A&P1. So looking at this map, We want to remind ourselves that the sympathetic nervous system exists. It's one of the two branches of our autonomic nervous system, which is the part of your nervous system that does basically automatic processes. It's working in the background without you thinking. We have the sympathetic effects, which are usually our fight or flight responses. We had our parasympathetic effects, which were our rest and digest kind of effects, as our brief rhyming summary of what these parts of the nervous system do. So what we want to note here, and remember right here, so our sympathetic nervous system, we have our chains of neurons. We have a preganglionic neuron, we have a postganglionic neuron, and our sympathetic nervous system is going to be giving off norepinephrine. It's going to be received by adrenergic receptors on our effector organs. Okay. And it also has a relationship to our adrenal glands, which sit on top of the kidneys. We have a modified sort of postganglionic neuron there, which is called a chromatin cell because it's been modified. It's there in the adrenal medulla, and it gives off epinephrine, which we can kind of think of as a sort of bridge between our hormones and our neurotransmitters. So epinephrine, norepinephrine related to our sympathetic nervous system. They're all going to be part of our flight or fight response and part of our stress response, basically, pretty generally. So thinking about this, because we are about to think about those adrenergic receptors in their effector organs, because the vasculature is one of your effector organs. So smooth muscle in our blood vessels is going to have these adrenergic receptors, and it's going to be responding to norepinephrine and epinephrine. So when we're controlling our arterioles by extrinsic mechanisms, it's largely going to be through sympathetic activity, as well as through some related hormones. So we're still just talking about controlling the radius of our arterioles in order to change their resistance. Right. So the sympathetic nervous system is the main part of this control. So if we're thinking about extrinsic control of arterial radius, and therefore also of our mean arterial pressure, we really want to feel pretty clear on our sympathetic nervous system. Okay. So to begin, our sympathetic nervous system does innervate the smooth muscle going to the arterioles. So we have nerves branching from this part of our nervous system all around those arterioles. Okay, so it's going to be giving off, mainly it's norepinephrine, because that's the part that comes from those postganglionic fibers of our sympathetic nervous system. Okay. Now, in most of your body, the smooth muscle of the arterioles has alpha adrenergic receptors. We're going to have adrenergic receptors in all of the smooth muscle in the arterioles in order to receive that norepinephrine or epinephrine. But most of the body, it's specifically the alpha type. And I'm going to pull up the chart of our different type of adrenergic receptors in a second. Okay. So that's important to know, because I'm saying most of your body, because we're going to have a big exception. And it's going to make a difference for how this works. So what we want to know right now is that when norepinephrine, coming from those postganglionic fibers of our sympathetic nervous system, binds to an alpha adrenergic receptor, the response is going to be vasoconstriction. You're stressed out, you're about to run away from stuff. Most of your body is going to sense that norepinephrine that you're giving off from your sympathetic nervous system. It's going to bind to an alpha adrenergic receptor, and your arterioles are going to clench down. The radius is going to become smaller, vasoconstriction, okay, increasing our resistance in most of the body. So in most of the body, we have vasoconstriction because we're increasing resistance by decreasing the radius when we bind our norepinephrine into these alpha adrenergic receptors. So because this is happening in most of the body, we're going to have an increase in total peripheral resistance. So an increase in TPR, because TPR is just adding up the resistance throughout our whole system. Okay. Now, it is also true that this is going to increase your mean arterial pressure, right? Because we just saw, we'll write the small version, right? But we just did our mean arterial pressure equivalent to, well, we can do the whole thing, right? Stroke volume, heart rate, which is our cardiac output or our flow together, plus our total peripheral resistance. All right, so if we've just increased resistance everywhere in our body, almost increased resistance, we're increasing our mean arterial pressure. So this is the largest effect that we're going to see. So sympathetic control of arterial radius. We're thinking about those alpha adrenergic receptors. So here's a reminder about those adrenergic receptors because we're about to talk about one of our other types. Okay, so this is just a chart from your book. You've seen it a couple of times before, but we're going to poke in and look at what we're interested in right now. Okay, so we're thinking about our alpha adrenergic receptors just now. So we can see here, tells you that they're in vascular smooth muscle. So now we know that that's that smooth muscle around our blood vessels. So we can see that our alpha adrenergic receptors have a greater affinity for norepinephrine, which is what we were just talking about as our main neurotransmitter coming out of our postganglionic sympathetic neurons, okay, norepinephrine, from our alpha receptors. The next adrenergic receptor that we're going to be interested in, though, is that we're going to have some blood vessels. Right, so some blood vessels are going to have beta-2 adrenergic receptors. You can see that one of the big differences here is that the beta-2 adrenergic receptors are going to far prefer epinephrine, which was what was coming from the adrenal medulla. So that adrenal gland sitting above your kidney. So we're about to talk about that part, where those are and how that makes a difference. And I'm going to have a little small version of the important parts of this slide for us and in the corner while we talk about it. So throughout your body, you have alpha receptors in your smooth muscle around your arterioles. But when we're talking about arterioles specifically in your skeletal muscle, so like your named muscles, the muscles that move bones, and in your cardiac muscle, so in your heart, they may have some alpha receptors, but it's mainly going to be those beta-2 receptors. So those beta-2 receptors are for your heart and for your skeletal muscle, okay? This is going to make a difference because we are going to see different effects when we have things binding into those beta-2 receptors, okay? So when norepinephrine binds to alpha receptors, we just talked about this happening in most of the rest of your body. This produces vasoconstriction, which decreases radius, raises resistance, therefore raising TPR and raising MAC, mean arterial pressure. Okay. But when we add in our understanding of those beta-2 receptors, things get a little more complicated. The other thing that gets really complicated is as we start to think about the other hormone, the other neurotransmitter related to our sympathetic nervous system. So most of our pathways for our sympathetic nervous system were giving us norepinephrine at the end, but that middle pathway where we go to the adrenal gland gives us a bunch of epinephrine produced by the adrenal gland. Right, so that's also known as adrenaline, okay? Now, that epinephrine binds to both of our receptor types, right? So we can see epinephrine will bind to an alpha receptor, right? But what it really, really likes to do is it really, really likes to bind to those beta-2 receptors. And those beta-2 receptors far prefer the epinephrine, although they could, under some limited circumstances, bind to the norepinephrine. If there's epinephrine, they really want that instead. They have greater affinity for epinephrine. So the effect of epinephrine binding to an alpha receptor versus a beta-2 receptor is different. When we're thinking about those alpha receptors, so the alpha receptors here, right, they're just still going to vasoconstrict, right? So you have norepinephrine bind to an alpha receptor, vasoconstriction. You have epinephrine bind to an alpha receptor, still vasoconstriction. Just if something's binding into that alpha receptor, you're creating vasoconstriction at that arteriole. Right? It doesn't really care which of our molecules is binding in. But at those beta 2 receptors, which are almost entirely just responding to epinephrine, when something binds in, they're going to create vasodilation. So the beta 2 receptors are responding in the opposite direction than our alpha receptors did. Okay. So this means that if you have a bunch of norepinephrine circulating around, it's probably going to our alpha receptors because our beta 2 receptors don't really like norepinephrine, which means you're going to have vasoconstriction. But if you have a bunch of epinephrine floating around, you're now going to have to think about what is the stronger effect, right? Because epinephrine really likes those beta 2 receptors, but it'll also bind into the alpha receptors. So that's where we have to think a little critically, and we're going to see that the effects of epinephrine in your body are going to be concentration dependent. So they're going to depend on how much epinephrine is in your body. So the epinephrine prefers beta 2 receptors, but it can bind to our alpha receptors. Okay. So this means that the effects of epinephrine are going to be concentration dependent. So if you have just a little bit of epinephrine, it has a really high affinity for that beta 2 receptor. So it is just going to go and bind to beta 2 receptors. So because it's binding to beta 2 receptors at these low concentrations, at low concentrations of epinephrine, the effect that we're going to see overall is vasodilation, because that's what the beta 2 receptors do. So the beta 2 receptors in your skeletal muscle, in your heart, respond even to really low amounts of epinephrine. And what they do when they sense that epinephrine coming from your adrenal gland, they dilate, more blood goes to your skeletal muscle and goes to your heart. Like, big picture, that's what's happening. At a higher concentration, you start to have spillover, essentially. So this lower concentration of epinephrine, you just had a little bit bound to those beta 2 receptors in the heart and in the skeletal muscle. Vasodilation happened at those locations. They got a little more blood flow. All is good. As you start to ramp up the epinephrine, you only have so many beta 2 receptors. They're essentially kind of getting full, right? So now you're going to see those epinephrine molecules also binding into the alpha receptors, because if there's lots and lots of epinephrine, those alpha receptors can soak it up, essentially. Okay. So we already had the vasodilation starting at the low concentrations in the skeletal muscle and in the cardiac muscle. Right, so that started when we had a little bit of epinephrine, and that's going to keep going, right? But you don't want the epinephrine to suddenly drop your blood pressure way down as you're getting tons and tons of epinephrine because you're really stressed out, going on a run, fighting a bear, whatever, right? So this is why it's important that when you have lots of epinephrine, we start to have vasoconstriction in other parts of the system as we have spillover to those alpha receptors. Okay? So the alpha receptors vasoconstricted in response to norepinephrine. They do the same thing in response to the epinephrine. So the effect there at those alpha receptors is increasing total peripheral resistance, which means that essentially the effect in these high concentrations of epinephrine is to kind of make up for the vasodilation that's happening at the skeletal and cardiac muscle. All right, because if you start out epinephrine to skeletal and cardiac muscle beta 2 receptors, they dilate, you get a lot of blood flow, your blood pressure's dropping, you would fall over if you don't make up for that, right? Like dropping blood pressure is going to be a problem, going to cause dizziness, falls, as we saw that man at the beginning explaining to us his issues with blood pressures, right? So we want vasoconstriction to happen. That's going to happen out in your other your other vascular beds in order to make up for this. So that's why it says that the dominant effect is usually vasoconstriction. So as we're going up to those higher levels of epinephrine, there's more of the rest of your body other than just the heart and the skeletal muscle. So they make up for it and can go like even a little bit overboard. And it's actually good for your overall. I realize this is like a little confusing the first time you see it. So any questions at this point, we will practice a bit with this in the future. So over the weekend, as you're studying this, do try explaining it back and forth to each other, because finding the right combination of words that makes this click in your brain is a task. And it will click at some point if you think about it hard enough, but I'll try to repeat it in as many different ways as I can think of, but your friend might come up with a better combination of words than I can. Okay. So essentially, this is what's happening when we are exercising as well, right? So our overall cardiac output is increasing during exercise. And we know that partially from our understanding of the heart, right? We talked about sympathetic effects on the heart itself. We talked about effects on stroke volume. We've talked about effects on heart rate. Basically, that both of them go up in response to sympathetic activity. Right? So the cardiac output is going up. And the resistance we've just mentioned is going to be dependent on what tissue we're talking about, because it's going to be dependent on what receptors are responding. So when you're exercising, skeletal muscle and heart, their blood vessels mainly have those beta-2 receptors. So they're really just going to respond to whatever epinephrine you're giving off. They're going to dilate and therefore send lots of blood to that skeletal muscle and heart. Elsewhere in your body, you mainly have alpha receptors. So they're responding to norepinephrine with vasoconstriction, but they are also responding to any epinephrine with vasoconstriction. So overall, they're constricting, raising resistance. Okay? All of this kind of together is what created those two different pie charts, right? So we've basically shifted blood from your GI tract, from your kidneys, from other parts of your body to your muscles and to your heart by expanding those arterioles, by dilating those blood vessels, sending more flow to those locations, the skeletal muscle and the heart, and constricting everywhere else. So we're sending less of the blood to these other areas. Tack-on concept is just hormonal control. So epinephrine does count as a hormone. So that works the way we have just discussed. So it's released from the adrenal medulla. It binds to mostly our beta-2 receptors in the skeletal muscle in the heart. So that's what it's going to do at those low concentrations, going to vasodilate there. At higher concentrations, it's also going to start to access our alpha receptors, causing vasoconstriction elsewhere in the body. Okay. So our two new tack-on concepts for hormonal control are vasopressin and angiotensin II. Vasopressin, or ADH, is one of our hormones secreted by the posterior pituitary. So we spent a lot of time thinking about the anterior pituitary when we talked about the pituitary gland and the pituitary and the hypothalamus. So this is the other one, the posterior part of the pituitary. We'll talk about vasopressin more when we get to the kidneys. One of its main jobs is to increase water reabsorption by the kidneys. As it is doing this, it also has this kind of secondary effect of vasoconstriction, therefore decreasing radius and increasing resistance throughout our system. Okay. Angiotensin II, another hormone, also causing vasoconstriction, also increasing total peripheral resistance. And I think we will also talk about angiotensin II as we talk about our kidneys and their overall effects on blood volume. Okay. So fortunately, these additional hormones, both are doing the same thing basically, right? They're both for our purposes, for cardiovascular purposes, they're doing vasoconstriction, raising resistance. So we're going to move over and briefly talk about our capillaries. So our goal for the capillaries is to understand what they are, what they look like, their anatomy, where we'd find them. Then we're going to be thinking about how we control blood flow through those capillary beds. And our big topic for capillaries ultimately is going to be how we actually move things between the blood and the tissue across our capillary walls. So if we don't get there today, that is a topic to preview over the weekend, because that's our next kind of like chunky topic. To our intro to capillaries, our capillary anatomy. So this is where we're exchanging things between our blood and our tissue. We've already seen one of the things that we're exchanging, right? We saw our oxygen and our carbon dioxide crossing the capillary walls. And we're having those local intrinsic regulatory effects on the arterioles. And we're going to see other things moving across as well. Lots of fluid movement we're going to be thinking about. They're small, 5 to 10 millimeters in diameter, or sorry, I think that's probably supposed to be micrometers. Anyway, regardless, there's a small diffusion difference. They are small. They're actually only 1 cell layer thick. So this is going to make it far easier for things to cross our capillaries rather than crossing, say, an arteriole or an artery or something, right? So they're not going to have this smooth muscle layer that we've been talking about. They're not going to have like a connective tissue elastic layer around the outside. They're just going to have this 1 cell layer, nice and thin, so that we can control a little bit what's crossing, but really make it very easy for us to exchange materials. Okay. There are also lots of them. So the capillaries have huge beds throughout your body. So all these like vast squiggly looking networks. So they have the total the greatest total cross-sectional area. So like if you took every capillary in your body and like lined it up and then sliced through it, you'd have a greater area than if you did that with any of your other types of blood vessels. Not really sure why you would do that. But this is just really emphasizing that there's a lot of them. Basically, there's a lot of them. The blood can really spread out as it gets to the capillaries. This means that as it's spreading out, it can slow down, allowing us to exchange material better. We also know that it's helpful to us that we have just kind of slowed down the blood coming out of the arterioles as we had this huge pressure drop across our arterioles because of their resistance. So this is all about enhancing the ability for your capillaries to exchange materials across them. So you have 10 to 40 billion in your body. The total surface area is about 600 meters squared. So lots and lots and lots. Most cells are within a millimeter of a capillary. They're all very short also. Capillary is about a millimeter long. Okay. Now, when we're talking about the capillaries, and start drawing a little bit. I'm going to draw a cross section. So we're really just going to be talking about 1 layer of cells. Okay, so this is a layer of endothelial cells. Okay, we're talking about our endothelial cells, making a nice circle. Okay, I'm not going to draw the rest of it, but imagine where I drew that line, we had more cells. Okay, so there are going to be some pores between the cells. So depending on the type of capillary, you may be able to move some things between cells, pores between those cells. Other things are going to be forced to travel across the membrane of the capillary. So specifically, right, we have this endothelial cell. So it'd have to go across one membrane on one side into the endothelial cell, across the other membrane on the other side to get into the blood. Okay. So some of the things are going to be regulated, some of the things are not going to be regulated. A capillary bed is just a bunch of these all together, a big network of capillaries. We saw some when we thought about our portal systems when we were talking about our endocrine unit. Okay. So those were 2 capillary beds we looked at. So here we see a graph of the cross-sectional area and the velocity of blood through the vasculature. So we can see that as we're getting towards the capillaries, we're getting a greater and greater cross-sectional area. because our tree is essentially branching more and more and more, right? And those branches, even though individual ones are small, add up together. And as we have greater area, as we have more room for that blood to spread out, essentially, this means that our velocity, so how fast that blood is flowing, can go down. Okay. So essentially, that's just pairing up those two concepts. So you have more capillaries, more room to spread out, your blood can go slow without impacting that total flow equation, right? Because it's not going to go very far, because they're going to merge back together. Okay. So we're going to have two types of capillaries that we're going to think about. Frankly, we do mostly think about our continuous capillaries, okay? That's because they're the most common. So if someone just says a capillary, you should assume they're talking about a continuous capillary. The gaps between the endothelial cells in your continuous capillaries are pretty small. So I'll draw this smaller, make a smaller radius. This will be faster. Okay. So we're going to have small gaps between our endothelial cells, right? So our gap here is relatively small, okay? So it's going to be able to pass through here is basically stuff that can dissolve in water, right? So small water soluble molecules, so hydrophilic things that are small enough are going to be able to pass along through here, but everything else, we're going to have to transport it across those endothelial cells if we want to move it. The fenestrated capillaries are different in that they have bigger gaps. So fenestra is a window. So fenestrations are big windows. So we just see endothelial cells that are essentially more spread out if we were thinking about a fenestrated capillary. So go like that or something. So we'd have much larger gaps, allowing much larger things to go through. So depending on what system you're talking about, this gap could potentially be large enough for a protein or maybe even a blood cell to go through. So this isn't going to be the case for most of our systems that we think about, but it is important in a couple organ systems in your body. So it's worth knowing that they do exist, these fenestrated capillaries where we can have larger things move. If we wanted to get larger and larger and larger gaps, eventually we'd move into discontinuous capillaries and sinusoids, which are kind of their own thing. Sinusoids you especially see in like, I think the liver, but those are really beyond the scope of this course for right now. Mostly, we're going to be thinking about our continuous capillaries. So continuous, their cells are continuous with each other. They're nice and close together, even though they do have some little pores. Before we talk about what exactly is moving through those pores or what is moving across those endothelial cells, we do want to think a little bit about how we're controlling blood flow through the capillaries. Okay. So we are partially going to use our arterioles and their resistance, right? Because we've been talking about how we can change the radius of the arterioles, change that resistance in order to direct blood to specific organs. Right, so that is essentially directing it to specific capillary beds. But we're also going to see some smaller structures. One of them are meta-arterioles, which are going to act kind of as a shunt across a capillary bed, as well as something called our precapillary sphincters, which a sphincter is something that constrict. So you can imagine what that might do. We'll take a look at how that can also kind of reroute blood around our capillaries. I like to look at it with a picture because I'm a very picture-focused person. Okay. So our arterioles, we talked about previously, you can decrease the radius, vasoconstrict an arteriole, make it nice and skinny, would make high resistance. So not much blood would get to whatever capillary bed came next because you just kind of cut off blood there. Or you could do the opposite. Vasodilation in the arteriole would send a lot of blood to those capillaries. So we're going to pick up with this next structure that we haven't talked about, a meta-arteriole. Okay. So what we're looking at, we have coming down the left, we have blood coming through our heart, through the arteries. Now it's in an arteriole. which has smooth muscle around it in the walls. And this is our overall capillary bed, this stuff, right? So we see our capillaries here. And on the other side, eventually our blood is coming out through a venule, then into a vein, then back to the heart. So what a meta-arteriole does is that when you have blood coming from the heart through an arteriole, the path it travels is hopefully at least some of the time going to be just through these capillaries, right? I'm just traveling some random pathway through these capillaries, pretending I am a red blood cell. Now, what a meta-arteriole does is it's like, like an overpass or something on a highway, right? So you can come down the arteriole, and if this meta-arteriole is open, you can just skip the whole capillary bed, go into the venule, into a vein, and back into the heart. So that's what we mean, that it's a shunt that allows us to bypass capillaries. So we don't even have to go into the capillary bed at all if we can access a meta-arteriole. Now, this means sometimes we're going to want to be able to skip that capillary bed, and sometimes we are not going to want to skip that capillary bed. So the meta-arteriole within it has smooth muscle that can open it up or close it off. So if you imagine this squeezing down, creating a little skinny radius, right? You could close off that meta-arteriole. And then the blood would have to go through a capillary because it can't go through the meta-arteriole anymore. Or you could have the reverse. You could have it dilate, make it nice and bulgy, nice and way wide. Now we have a like really wide highway through. So you're making it a little less likely that you're going to go through the capillary bed, and instead you'll just skip it. Okay. So we will pick up here next time. I do recommend that in preparation for next week, you look a little bit at the concept of filtration and absorption, because we're going to be going through a bunch of forces and equations for things moving across capillaries next week. Otherwise, you have a quiz on what we've done this week for Monday. That's up and open, I believe. If it's not, let me know and I'll change the settings, but I think it should work. I'll see you next week.